I've got a problem here that I want to do three different ways for you. This is a calculation of work done. Okay, so the situation is this: we got a mountain climber that's just climbed to the top of a very steep cliff, and the rope is still hanging out over the side. There's 50 meters of rope, and that rope weighs a total of 5 newtons. The question is, how much work is done to lift all of the rope up to the top where the climber is? I want to know, what is the work to lift the rope? Now, I'm going to do, as I say, I'm going to do this three different ways because each of you is going to have a different way that sinks in, the way that you see it best. I'm going to do it first, just like the leaky bucket problem in the last video. So I'm going to set up essentially a coordinate system here. I'm going to say y equals 0 down at the bottom. I'm essentially setting this as my benchmark. When all the rope is out, this is where the bottom of the rope is. And as I lift it, the bottom will be at whatever the y value is. So by the time the bottom of the rope gets up to here, since it was 50 meters long to start with, this will be y equals 50 up the top. So essentially I'm thinking of this as what's the elevation of the bottom of the rope? When it's all the way out, the elevation is at 0. When the rope is all the way lifted, the elevation of the bottom of the rope is now up at 50. Okay? So if I look at the weight that's out there, when all of the rope is out there, so when let's say y equals here and the weight, so force is there, when y is equal to 0, all the rope is hanging, all that rope is hanging, and there's 5 newtons of weight on it, right? Then when the rope is all the way up at the top, the bottom of the rope is made it all the way up at the top, so when y is 50, the weight that's still hanging out there is 0. And I think you can agree with me that that the weight is a linear function of how much rope is hanging out there. So I expect that this would be a straight line joining those 2 points. I can then come up with an equation for that straight line where the force is equal to, the intercept is 5. The slope is a rise of -5 for a run of 50. So that would be negative, let's go do a little work on the side, 5 over 50, that's the same as 1 over 10. Right? So 1 over 10, actually, I think I'll write as 0.1 times y. Just going to do a quick double check that that works. When I plug a 0 in, I've got 5 minus 0, so that's 5. If I plug a 50 in, well, 50 times 0.1 is 5. 5 minus 5 is 0. So, all right, I like that. It's funny, as I'm making this video, I say, I got the answer, and I actually gave myself a thumbs up, but you can't see my thumbs up, saying, yay, it worked, all right? I got this right values on each end, so I think my formula is good. So now, like that leaky bucket problem, I'm looking at this saying, if you've got all that rope hanging out there, all 5 newtons of it, and you lift it up just a tiny little bit, so now the end of the rope is right there, so you've lifted it up a distance dy, then the work that you just did was all that weight, was all this weight of 5 newtons times a little tiny bit of lift dy. Right? And then you're going to lift it up again that next little bit, but you didn't have as much weight out there. You only had this much weight now, and so that weight times that displacement is the work done. And you just keep doing that until all of the rope has been lifted all the way up to the top, and you add up all these little bits of work. Well, you're just finding the area underneath this force function. So this is the integral, the work done here is the integral of 5 minus 0.1y times dy. 5 minus 0.1y is the weight of the rope that's hanging out there when the bottom of the rope is at some elevation y. dy is the distance that is lifted. This much force, that much lift, it's work done. What values of y are we interested in? Well, we're interested in all the way from y equals 0, when all of the rope is out, to y equals 50 when none of the rope is out. And then I need to type that into my calculator and see what I get. And so I'm going to do that very quickly off the screen. So I get 125. That would be in joules. And actually, as I get that, as I calculated that on my calculator, all of a sudden it hit me. It's like I'm finding the area of a triangle. I ought to be able to do that with a base of 5 and a height of, sorry, base of 50 and a height of 5. The area is 1/2 the base times the height. So 1/2 times 5 times 50, or let's say 5 times 25, which is 125. Anyway, so 125 joules. Now, I want to do this problem a different way. So this time I am going to set this up where, same picture. So still got this mountain climber celebrating at the top. This is hanging out. This time I'm going to let y equal the length of the rope that's still hanging. So essentially that means when all of the rope is out, I've got y equals 50 down here. If the rope is hanging all the way down to there, there's 50 meters of rope out. If all the rope is pulled up, well, then there's nothing held out. So if I mark this scale this way, from 0 at the top to 50 at the bottom, whatever y value is here, that's how much rope I'm measuring essentially from the top down, where in the previous example, I was measuring from the bottom up, right? Y was being measured this way here, y is being measured this way here. It really isn't going to make any difference which way I do it, as long as I stay consistent within my method here. So why is the length of the rope still hanging? I can figure out how much that weighs because I know that it's 5 newtons per 50 meters. So 5 newtons per 50 meters, and if I multiply that by y meters, I get 0.1 y newtons. So this 0.1 y is telling me how much, if the rope is hanging down to here, then this is the amount of weight that is hanging there. So then I'm going to take that weight and lift it. Lift this weight a tiny little bit. Sorry, weight, W-E-I-G-H-T. Lift this weight a distance of dy. That is, change the amount of rope that's hanging by just a little bit. So you lift it up a little bit, now there's less rope hanging. Right? So if we lift this distance, so is this much weight, that much lift, the work done, the work is 0.1 y times dy. Distance lifted times the force. Force times distance is work. So the total work is all those little bits of work that you do as you lift each little bit. So the total work is going to be the sum of all these things. 0.1 y dy. And what values of y am I interested in? Well, I'm interested in when there's nothing hanging to when all the way down to when there's 50 meters hanging. So 0 to 50. Now, this is curious to me because this is a different integral than that last one, right? This here was this, and if I said 0 to 50, I wrote 0 to 5, 0 to 50. This function here that I'm integrating is different than that one. But if I look at the graph of that function, I'm looking at this right here. So from 0 to 50, I've got 0.1 times 50. That gets up as high as 5. And what I'm doing is I'm looking for the area underneath here. Well, it turns out that the area underneath that, I got a base of 50, a height of 5. This is still going to be 125 joules. I was calculating the area of this triangle over here, 5 tall, 50 wide. Now I'm calculating the area of this triangle, 5 tall, 50 wide. Where one I was doing this diagonal, now I'm doing that diagonal. Anyway, the area underneath is the same. The thought process is a little different. And as you set a problem up, you just have to decide, how am I working things? Am I measuring from the bottom up? Am I measuring from the top down? And then use that. All right, I've got just under 5 minutes to do a third way of doing this problem. So setup's the same rope. Here's my celebratory mountain climber, and the rope hanging down all the way down to 50 meters. This time, what I'm going to do is I'm going to measure again from the top down, so y equals 0 to y equals 50. Essentially, what I'm thinking is I'm going to take this rope and cut it up into a bunch of little pieces. All the same length. Each one of these has a little bit of length dy. What I'm going to do now is I'm going to say, how much weight is there in that tiny little bit of rope, and then how far do I have to lift that piece? Okay, so the length of each piece, let me write it that way, length of each piece, I'm gotten ahead of the computer here, length of each piece is dy. So the weight of each piece is 0.1 times dy. And remember that 0.1 came from the calculation up here that we did. We knew that the total was 5 newtons. The total length was 5 meters, so it's actually 0.1 newtons per meter. And so if the length of the piece is dy meters long, then dy times 0.1 should be the weight of that piece. Now, how far does this weight have to be lifted? Well, the weight that's here at the top with y equals 0 doesn't have to be lifted at all. The weight that's down here with y equals 10 has to be lifted 10 meters. The weight that's down here, that's 50 meters down, has to be lifted 50 meters. That is, y is the distance that it has to be lifted. And there, catch up. So the work done to lift each little piece, a little bit of work, is y, distance lifted, times the weight, 0.1 dy. And then I want to add all those up, all those little pieces. I want to add up all those little bits of work. So I have little bits of rope everywhere from y equals 0 to y equals 50. And the work done is 0.1 dy, sorry, 0.1 y dy. Okay. Which is exactly the same integral as I had on this previous method, but I got it in a different way, right? And I show you 3 different ways because each of the problems that we do, you may find one method more intuitive than the other, and so that's what you use. Although I ended up with the same integral on these two, on this one, the dy was used in the weight. I had essentially equal pieces, all the same weight, and they were lifted varying amounts, right? That the one here didn't get lifted as far as the one down there, but they all weighed the same. Every little piece weighed the same. Up here, I was thinking in terms of the lift is all the same. Each time you lift it by a little bit dy, but the weight on each lift changed. So there was a varying weight with constant lifts, and on this one down here, I had constant weights with varying amounts of lift. Right? Either way, I get the same 125 joules. And my computer is really slow at the moment. So there you go. We'll do some more problems in subsequent videos.